Hello everyone. So today we are going to start our first chapter in analog electronics, that is diode circuits. Okay. So in diode circuit, before understanding the diode circuit, we have to study some basic semiconductor physics that we have already studied in 12th class, but many of the students skipped this topic. So that's why I thought I should again teach you this topic. Okay. So this will be the first class, and in the second class we will be studying diode circuits. But here we will study some basic semiconductor physics and PN junction diode. Okay. So based on the conductivity, materials are of three types. This is what we study in 9th 10th class. So these are of three types: conductor, semiconductor, and insulator. Conductor, that allows the flow of charge, like the current flows in them. Insulator hardly allows the flow of charge, the current doesn't flow. And semiconductor, in between conductor and insulator, moderately allows the flow of charge. And if you want to increase the conductivity, you introduce some impurity in them. If you introduce some impurity, they will conduct. What is that impurity? That we will see. So basically, conductor allows the flow, insulator doesn't allow, and semiconductor in between. And semiconductor is highly used in electronics industry. So we will be studying about semiconductors in complete chapter. Okay. So this is the most important point. Examples you can see. What are the example of conductors? That are copper, brass plate, steel, and gold. And insulator, glass, air, wood. From wood current doesn't flow, from glass current doesn't flow, right? And what about semiconductor? Silicon, germanium, gallium arsenide. All these are example of semiconductors. Okay. Now let's just take the example of semiconductor. Now we'll be studying about semiconductor only, not about conductor and insulator. Forget about conductor and insulator. Now only semiconductor. So let's just take the example of silicon. So in silicon, what is the electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6. If you don't remember, then you don't need, no need to worry. Okay. So this is the outermost shell, right? This is the outermost orbit. So how many electrons are there? 4 electrons. In the first one 2, in the second one 8, and in the last one 4 valence electrons are there. So now these 4 electrons can make a bond. Do you get it? These 4 electrons can give their electron to some other atom, some other silicon atom. So these 4 electrons will make a bond. So let's just make the crystal of a silicon. Okay. So let's just assume this is our silicon, which is having 4 outermost electron. Okay, 1, 2, 3, 4. Now these four electrons can make a covalent bond. So let's just assume near to it we have another silicon atom. This is also having 4 electrons. Okay. So now these two can make a bond, right? Similarly, this electron can make a bond with some other silicon atom. Similarly, this can also do this. This can also do this, right? So let's just assume there is one more silicon atom here, which has an electron here. 4 electrons are there in outermost cell, so they are making bond. Okay, here as well there are 4 electrons, so they are also making bond. Similarly here 4 electrons, so they are also making bond. Okay, so in the same way these silicon atom also make a covalent bond. Okay, this bond we call is as covalent bond. Covalent bond. Okay, so this can happen, they can also make bond. So this is the crystal structure of a silicon, right? Now this is the condition at T equals to 0 Kelvin. What do you mean by 0 Kelvin? 0 Kelvin, K equals to C plus 273. That means how much degree? Minus 273 degree. This is the condition at minus 273 degree Celsius. Okay. So now what happens for a temperature above 0 Kelvin, or what you can say at room's temperature? Okay, at room's temperature. What is typical room's temperature? At room's temperature. What is typical room's temperature? 300 Kelvin, right? Or 27 degrees Celsius at room's temperature. So due to thermal energy, these are not free electrons, right? Because they are forming covalent bond. They are forming covalent bond with each other, so they are not free electrons. So due to thermal energy, these electrons may get out of air. Okay. Like there is some energy in the to the crystal at room temperature. There will be some energy to the crystal. Okay, so then these electrons can get out of there and create a vacancy there. So what is that vacancy called? So what will happen, that we will see in the next slide. So what will happen, this electron will get out of here. Okay, so this electron will get out of here, and what it will create, it will create a vacancy here. Okay, the electron went out of here and it will create a vacancy. Okay, so now what is this? This is a free electron. What is this? This is a free electron. This is a free electron and it created a vacancy. That vacancy is known as hole. Okay, what is hole? Absence of electron. Basically, what is hole? Absence of electron. So we will be using this term again and again, electrons, hole, electrons, holes. So what are electrons? You already know. Now if electron is getting out of the covalent bond, then it creates a vacancy there, and that vacancy is known as hole. Okay, so hole is denoted by a round sign. So basically this is your electron. Okay, this is your electron, and if there is this vacancy, that means we call it hole. Okay, now what happens, because there is this vacancy, now this electron can go here and complete this vacancy, and now if this electron is going here, this will create a hole. Now what happens, this electron may come and go there, now this will create a hole. Are you getting my point? What do I mean is that, let's just assume there are these electrons, 3 electrons are there. Okay, now if this goes out, that means it will create a hole. Okay, now this electron is here. Now what happens, this electron may come here at the vacancy of hole, so it will fill this and will create a hole, right? Like this electron is coming here and created a hole here, and this that is electron, that free electron is outside there. Again this will come here and it can also create a vacancy. This free electrons remain there. So basically hole is nothing but the absence of electron only. Okay, hole is not a like something different. So this is just a vacancy of electron, that is known as hole. Okay, since this is free electron, so this is known as charge carrier. Okay, charge carrier. Now the question is, let's just assume I have a piece of silicon. Now the question is, will there be any current? There is no supply I am giving, I just have a piece of silicon in my hand. Now I am saying there is this free electron. So is this electron able to generate a current? What is happening in this circuit? Not in the circuit, in the crystal, what is happening? This electron is getting out, so it is creating a hole. Now this electron is going here, it is creating a hole here. Now any electron may come and then it may create a hole there. So the motion of hole and electrons are random here. If you are not applying any electric field, the motion of holes and electrons are random, and because of this random motion you can't generate any current. So if you are just having a silicon, a piece of silicon in your hand, it will not generate current. Okay, you have to give some supply. So because of this random motion there won't be any current. Okay, this is just a doubt anyone can get, so I just solved it here. So let's just see the types of semiconductor. So there are two types of semiconductor, intrinsic and extrinsic. Okay, extrinsic. Okay, intrinsic and extrinsic. Okay, so intrinsic is the pure semiconductor that we have already studied. This one, only silicon is there. In the complete crystal, only silicon is there. What is extrinsic? As extrinsic. So there are two type of extrinsic semiconductors, that are p-type and n-type. So when we introduce some impurity in the semiconductor, then it can be of two type, p-type and n-type. What kind of impurity, what is impurity, that we will see. So there can be two types, p-type and n-type. So what is p-type semiconductor? So we had this silicon crystal, Now what we do, we introduce trivalent atom. What are trivalent atom? If you remember, boron, carbon, nitrogen, and in carbon there was this row, this column was there, right? So in this column we had boron, aluminium, gallium, indium, and some TL was there, I don't remember. So this was the row. And for nitrogen, nitrogen and New Zealand, Pakistan, phosphorus, Australia, arsenic. So these elements were there, right? So when you introduce trivalent atom in the silicon, or in the semiconductor, here I mean semiconductor. Okay, so you are what you are doing, you are introducing trivalent atom. Now how many electrons are there in the outermost orbit in case of trivalent atom? Like carbon is having 4, boron will have 3, and nitrogen will have 5 electrons, right? This will have 5 electrons in outermost cell, this will have 4 electrons in outermost orbit, and this will have 3 electrons in outermost orbit. So it is having only 3 electrons. So now we are doping boron here. What do you mean by doping? Doping means introducing impurity, not something else. Okay, since all of you are engineers, so you know. So doping means introducing impurity. Okay, nothing else. So here we are doping. Okay, no one is soy bhaktare. No one will do doping. Okay, so introducing impurity. So we are introducing boron atom here. So let's just assume we are introducing boron atom in this. So it has only 3 electrons in the outermost orbit. Only 3 electrons are there. So let's just assume this electron is not there. So if electron is not there, that means there is a hole. Are you getting my point? Boron is only having, this is your boron. Boron is only having 3 electrons in the outermost shell. Same with the aluminium. Okay, aluminium is also having only 3 electrons. Okay, so instead of boron, I will prefer writing aluminium because of the bigger size. I will write aluminium here. So three electrons are there, and it is having one vacancy. So by adding impurity, what we have done, we have introduced what? We have introduced a hole. By just adding impurity, we have introduced a hole. So by adding impurity, what did you get as the output? Okay, now what can happen? These electron can travel, like these electron can travel here, and it will create a vacancy there. Then these may travel and create a vacancy there. So there can be motion of electron and holes. Okay, again, if you don't bias it, it will not generate any current, because still the motion are random only. Okay, so now what this aluminium is doing? Now this aluminium can accept electron, right? This aluminium has a vacancy of accepting the electron. So these ions are known as acceptor atom, you can say. These atoms are known as acceptor atom. Okay, because these can accept the electrons. They are not giving the electrons, they can accept the electron. Let's just assume we write Na2 plus. Why do we write Na2 plus? That means it is giving you 2 electrons, right? Now since they are accepting something, there will be a negative sign, right? Since they are accepting something, there will be a negative sign. And what they are delivering? They are delivering a hole. So this is how you denote a p-type semiconductor. Okay, you introduce aluminium, it has only 3 electrons, so they are making covalent bond. One vacancy is there, that will create a hole. Now this hole can accept the electron. So if it is accepting, like you are taking some money from someone, so you are at negative, right? The one who gives you money, that guy is at positive, and you are accepting money, that means you are taking money, that means you are at negative. So this aluminum ion can take electron, so that's why it is at negative. I took the example of Na2 plus. It can give you 2 electrons, So that's why there is plus. It is delivering 2 electrons, then there will be plus. Now it can accept electron, so there will be minus. So this is how we denote a p-type element, p-type semiconductor, that it can accept. So minus sign is there and hole is there. Okay, so this is negative and hole is kind of positive, because it is the vacancy of electron. Electron is kind of negative. Okay, so hole is kind of positive and it is negative. So positive and negative, that means it is electrically neutral. So basically every semiconductor, be it pure or impure or p-type or n-type, intrinsic or extrinsic, every semiconductor is electrically neutral. Okay, so here what I have written, aluminum can accept electron, so it will create a negative ion. So how will you denote a p-type? Negative ion accepting, and what it gives you? A hole. Okay, so this is how a p-type semiconductor can be denoted. So many people get confused why this is a negative sign there. That means it is acceptor. It is a acceptor atom. So p-type will be negative and a hole, because it is delivering a hole and accepting an electron. So negative hole, negative hole. Now what about n-type semiconductor? Here what we will do, we will introduce pentavalent atoms, because what is nitrogen? Nitrogen is having 5 electrons in outermost orbit. Okay, nitrogen having 5. Same with the phosphorus. Phosphorus is also having 5 electrons in the outermost orbit. So it can deliver a electron. Let's just assume I put the phosphorus here. So what it will do? It will deliver an electron. So 4 will make a bond. 4 of the electrons will make a bond, and 1 electron will be there. That will be free electron. So it will be giving us a free electron. Okay. So basically phosphorus is also giving us a giving us a free electron. So it is delivering an electron. So how it will be created? Positive sign and then a electron. So how you will show n-type semiconductor? Since it is delivering the electron, so plus sign and then plus negative, plus an electron, plus and electron, plus and electron, plus and electron. Now we have seen two things here. This is n-type, sorry, this was p-type and this is n-type. So what is this? These are ions. Okay, positive ion, negative ion. So these are ions and these are charge carriers which can generate the current. I will repeat this line. Okay, very important line. This plus and minus are ions and this hole and electron are charge carriers. Ions can never generate a current. Ions are immobile. Immobile means they will stay there, they don't move. Like if I am saying I have positive, positive, positive like this, negative, negative, negative like this. Maximum what it can do, it can generate an electric field. That's it. It will not generate a current. They are immobile. If the charges are not moving, in the basics of network, in the first lecture we have studied, when will the current flow? If charge move, ions are still, they are immobile, they don't move, they will not generate current. Ions doesn't generate the current, charge carrier generate the current. Okay, so always remember, ions never generate the current, charge carrier generate the current. And here this plus is the ion because it is delivering an electron. Okay, so that's why we call them donor atom. Okay, acceptor atom and donor atoms, because they are delivering an electron. Okay, so they are known as donor atom and we show it like this, plus and then a electron. Okay, this is the electron. So this is also electrically neutral, right? This is also electrically neutral. Why electrically neutral? Like sometimes in MCQs I have seen this question in AJ exams, that they ask like what is a p type? It is positive, negative, electrically neutral or something else. So all are electrically neutral because plus shows something plus and this electrons shows the behavior of negative. So they are electrically neutral. Okay, be it p type, be it n type, or pure semiconductor or pure silicon, everything they are electrically neutral. This is also electrically neutral. Okay, so let's just revise whatever that we have studied in this 20 minutes. First we saw that there are three types of materials, right? Conductor, semiconductor, and insulator. Based on the conductivity, conductor allows the flow, moderately allow, and doesn't allow. Example we have seen. Then in silicon there are 4 electrons. These 4 electrons in outermost bit can outer orbit, they can make the covalent bond. If they can make the covalent bond, so this is the pure silicon. Okay, and due to at the room temperature, due to thermal energy, some bonds are broken, so they create a vacancy there, and that vacancy is known as hole, and electrons are going outside. Okay, so this is a hole. Okay, that we call absence of electron. So hole is nothing but the absence of electron. Now semiconductors are of two types, intrinsic and extrinsic. Intrinsic we have studied, that was the pure silicon. Now in extrinsic there are two types, p type and n type. In p type, what do we do? We introduce trivalent atoms. Okay, so we do the doping of trivalent atoms. Now what they will do, they have only 3 electrons in the outermost orbit. So the 3 electrons will frame a covalent bond, and there will be one vacancy that will create a hole. So that is the charge carrier there. Because of this hole, some electrons will move here, and there will be movement of charge carriers. So this is the charge carrier there, that is hole. So since they are accepting the electron, so they will known as acceptor atoms. Okay, and since they are accepting, there will be a negative ion, and over it we will make a hole. Okay, so since they are accepting, we will make it negative. Okay, and in case of n-type semiconductor, what is happening? We are introducing pentavalent atoms. So let's just assume we have introduced phosphorus. So phosphorus will have 5 electrons in the outermost orbit. So 4 will make a bond and 1 will be free electron. Now since they are giving us the electron, that means they will frame a positive ion. So they are framing a positive ion, and we will show an electron there. So these are the ions and these are the charge carriers. In p-type semiconductor, what was the charge carrier? In p-type semiconductor, holes were the charge carrier. In n-type semiconductor, electrons are the charge carriers. Okay, and the ions are positive in n-type and ions is negative in the p-type. This is what you need to remember. Okay, and both are electrically neutral. You just need to remember, in p-type holes will be there, so you will make a hole, and since you know it will be electrically neutral, so you have to make a negative sign, because hole gives a positive sign, right? And similarly for electron, you will remember, for n-type they will give an electron, so electron you will make, so you have to make a positive sign. Since they are donor, so they will be positive. So this is how you make a p-type and n-type semiconductor. Okay, and when there is no external field applied across the semiconductor, it will not generate any current. Okay, so this is the basic introduction of p and n-type semiconductors. Now what we will do, we will combine these two p and n-type semiconductor, and we will see what is happening. Okay, now I am teaching this like in a very what do we say, not in a deep manner, because this is not useful for studying analog electronics, but this will be useful for EDC, electronic devices. So in that electronic devices, you will be studying this subject very deeply. Are you getting my point? Like, this is not everything that you have studied in semiconductor physics. In semiconductor physics, there are a lot of things. It will take around 25 hours to teach semiconductor physics only. So this is just the introduction that we need for studying analog electronics. Many of the teacher I have seen skipping this part, because device physics is not a normal thing. Okay, it takes a lot of effort to understand, and also to make anyone understand. It is very tough to teach device physics. Okay, and whoever teaches device physics, I have huge respect for them, because that is a very typical subject. Device physics is very typical subject. So we are just taking the overview, that's it, because electrical guys and instrumentation guys, and even for the placements, this much deep device physics will not be necessary. But when we study electronic devices, then we will study everything about the device physics of p-type and time, and I will teach that subject very deeply. Okay, so let's just move on to p-n junction now. So what we do, we are forming a p-n junction now, p-type semiconductor and n-type semiconductor. So what you need to assume, you just assume that we have just stick them together, that's it. How it is made, that information is not necessary, especially for analog electronics. Okay, So we just tick them that you should remember. Okay, so this is your p type and this is your n type. In p types there are this is how I denote p type and this is how I denote n type, right? So this is my p type semiconductor, this is my n type semiconductor. Now let's see what is happening. Look, there is one thing. Let's just assume in a room there are 5 people and all the people are standing in a corner. So what they will do? They will try to go to the lesser denser area, right? If 5 are standing in a corner, they will try to go in the lesser denser area where there is vacancy. So they will go towards the vacant side of the room, right? If you use a spray, what will happen? If you just click there, then the spray particle will move towards the lesser denser area, right? Are you getting my point? And same thing happens in the semiconductors as well. Okay, in semiconductor, in p type, what are the majority charge carrier? That are holes. Okay, because of impurity there will be some minority charge carrier as well, that will be electron. Like in this p type electron, in this p type semiconductor, how many holes you can see? 4 plus 4 plus 4 plus 4, 16 holes you can see. So there will be a few electrons as well. Okay, so I should write this thing here. So here I will write majority charge carrier are electrons. Majority charge carriers are holes, sorry, in p type semiconductor, and there can be some electrons as well. So minority charge carrier will be electrons. So in the process of formation, like when we are forming this p-n junction, okay, there can be some impurity, or while doping there can be some impurity. So there can be this minority charge carriers that are electrons. Okay, and here as well there can be some holes. Okay, so here what are majority charge carriers? These are electrons. Okay, and minority charge carriers are holes. Okay, so what I was saying, we will always try to go to the lesser denser area. Now what will p type semiconductor see? That there are a lot of holes. Now holes will try to diffuse towards n type region because there are electrons, right? So here there is more vacancy of electrons, here there is more vacancy of hole, and the not more vacancy of holes, we should say there are more holes at p type. So they will try to diffuse towards the n type because there are lesser holes, right? Holes will always try to go at that side where there is lesser density of holes, right? This is what we call that concentration gradient. Okay, so there is more concentration of holes and there is less concentration of holes. So because of concentration gradient, these holes will try to go towards the electrons and electrons will try to diffuse towards the holes. Like some people say that this is the electron, this is attracting the hole. No, this is not happening. The electrons are not attracting the holes. Okay, because of the concentration gradient, holes are moving towards the electron and electrons are moving towards the hole. No attraction, nothing like that. Okay, because of concentration gradient it is happening, because there is more concentration of holes and there is less concentration of holes. So because of concentration gradient, this lecture one is the most typical one. Okay, after that we will just see the diode as a circuit. So after that circuit solving will be there, so that will not be difficult for you. Like understanding the physics of the devices, that is very tough. Device physics is the most typical chapter of electronics or electrical combined. Device physics is the most complex topic. Understanding device physics is very tough. And as a designer you will not have to understand device physics. Okay, just to tell you, once you get into IITs or once you get into industry, you will not have to understand device physics. You will be given a device and you will just have to understand the characteristics of that device, how VI curves look like and this is what we will be studying in analog electronics. Device physics is different, that EC student will have to study, not electrical student. EC student will have to study, and if some electrical student is interested, then he will also study that. Okay, so yeah, what is happening? Yeah, I have written here unbiased. What do I mean by unbiased? Biasing means, what is biasing? Biasing means, this term will be used a lot of times, giving supply. Okay, voltage or current, just applying, giving some supply, that this is what we call biasing. Okay, if I connect a voltage across it, 5-volt battery, and this one is 0, let's assume, then it will be known as biasing. Okay, so I have written unbiased, that means there is no voltage across them. Okay, yeah, so due to potential gradient, holes are diffusing towards electron, and electrons are diffusing towards holes. So what is happening? This holes is going towards the electron, electron is coming here. So what it will do? They will become neutral. Holes and electrons both will recombine, and it will be electrically neutral. So this is what it will frame. Okay, electron moves towards p-type region and recombines with the holes, and holes moves towards n-type region and recombines with the electron. So what will happen? Now this much of region will become immobile. This much of region will have lesser charge carrier. It won't be that there is no charge carrier. There can be some charge carriers, like a small electron can be there, or a small hole can be there. So in this region there are only immobile ion in depletion region, and this region is known as depletion region. What happened? Electrons move towards n-type. Electrons are moving towards p-type region, and holes are moving towards n-type region. Both are recombining and framing a depletion region. Okay, and in depletion region, the number of charge carriers are lesser. Okay, in this region is known as depletion region because we can't see any charge carriers there. So in depletion region, what is present? Only immobile charge carriers are present. No, sorry, not charge carrier. Immobile ions are present. Immobile ions are present. There are no charge carriers. Okay. In depletion region, there are no charge carriers, only immobile ions are present. Now this is positive, this is negative. What will happen? It will generate a internal electric field. These ions generate E internal. This is what we are calling internal electric field. Internal electric field from n-type to p-type. So they are generating a internal electric field from n-type to p-type. Okay. Now there is one thing. Because of an electric field, let's just assume my electric field is in this direction, and there is a hole and there is an electron. Can you tell me where will the hole feel the force and where will the electron feel the force? Holes will always feel the force in the same direction as the electric field, and electron will always feel the force in the opposite direction. Because what is force? Force is equals to QE. electron is negative, so this quantity will be negative, right? So electrons will be feeling the force in the opposite direction and holes will be feeling the force in the same direction as the electric field, because F is equals to QE and holes are positive, so they will be in the same direction. So you need to remember this, electron will feel the force in the opposite direction of electrons. So this is a note, okay. Electrons feel force in the opposite direction, force in the opposite direction of electric field while holes feel the force in the same direction. In the same direction, okay. So this is what you have to remember. Now there is an internal electric field which has a direction like this. Now we have a hole here, okay, we have a hole here. Now where will, because now let's just assume this hole tries to go at that side, because of a concentration gradient this hole is trying to go towards the n side, n type, towards the n region, okay. Now what will this internal electric field will do? This is trying to go there, but internal electric field will give a force to the hole in this direction only. Are you getting my point? The hole is trying to move towards the n region, but since there is this internal electric field that will give the force to the hole in this direction only. So it will say go back, just stay there. So because of this internal electric field, neither hole nor electron can travel. Now let's just assume electron tries to go there. Because of this internal electric field, electron will feel the force and will have to stabilize there. So because of this internal electric field, no further electrons and no further holes will try to move, okay. So this, because of this internal electric field, there is this equilibrium in the p-n junction, okay. And is there any current? If unbiased p-n junction is there, unbiased means I am not giving any supply. So is there any current? No, there isn't any current, because this hole cannot go there, this electron cannot go there. So movement of charge carrier is not there. So this is the equilibrium. So there is no current is there, okay. Because of this electric field, the electron feel force in the opposite direction of the electric field and stay in the n-type region only, and these holes will feel force in the same direction of the electric field and will stay in the p-type region only. So this is the region this p-n junction doesn't allow any current to flow when it is unbiased. Are you getting my point? Okay. So these ions generate internal electric field from n-type to p-type. This internal keeps the equilibrium. Okay, this is keeping the equilibrium, okay. Hole is feeling the force in this direction, they remain there. Electron feel the force in this direction, they remain there. Now what I will do, so here I have written, in a p-n junction without any external field, without an external applied voltage, an equilibrium condition is reached in which potential difference across the junction in which potential difference forms across the junction. So this is a potential difference that is created. This is plus, this is minus, okay. So here a potential difference is created, and that potential difference is known as built-in potential, okay. So for silicon, built-in potential is 0.7 volt, and for germanium, built-in potential is 0.3 volt. Let's just revise what we have studied. P-type, n-type, combine them. An electron will try to go towards the go towards the hole, and hole will try to go towards the electron. Both will recombine and they will just recombine, and only ions will be left. Because of these immobile ions, there will be an electric field in this direction. Now this electric field will generate a force in the electron in the opposite direction. That means electron will remain there as it is, and holes will feel the force in the same direction. That means holes will remain there as it is. So an equilibrium is reached. So an equilibrium condition is reached, and because of this there is a potential difference created. Okay, because of this diffusion of electron and holes, there is a potential difference created, and that potential difference is known as built-in potential. So for silicon, built-in potential is 0.7 volt, and for germanium, built-in potential is 0.3 volt. So basically the majority charge carrier has to cross this barrier potential to generate some current. So unbiased PN junction will never generate any current. So now these majority charge carriers, these holes and these electrons will have to cross this potential. Okay, we'll have to cross this potential. That means we have to apply a stronger electric field. So that these electrons cross the potential. So what we will do? How can we apply electric field? By connecting a battery. So we will connect a battery. Okay, and then we will see what happens in the PN junction. So now what we are doing? So this was our unbiased PN junction. Now how do we denote it in the circuit? In circuit we denote it like this, and we call this as diode. Okay, so what is the structure? This is the structure. Okay, this side is known as P, this side is known as N. So now we have to bias our PN junction diode. So how we will bias? There are two techniques: forward bias and reverse bias. Forward bias means we will connect the P type to positive and we will connect the N type to negative. Okay, and in reverse bias, what do we do? The name by name also you can identify. Reverse bias, that means negative will be connected to positive, and positive P will be connected to, this is P, this is N. P will be connected to negative and N will be connected to positive. This is how we will bias. Are you getting my point? P is connected to positive, N is connected to negative, forward bias, and P is connected to negative and N is connected to positive. That means reverse bias. Okay, so let's just see what happens in the forward bias. So now we have given a battery of voltage V. One more thing, when it was unbiased, okay, now this is having charge carriers. This side is having charge carriers, right? This side is having charge carrier, this side is also having charge carrier. This is not having any charge carrier. That means this side is providing high impedance, high resistance, right? The depletion region is having no charge carriers. That means it doesn't allow the flow of charge carriers across it, right? Because of this internal electric field, this E internal that is shown here, because of this E internal electric field, the charge carriers were not able to move. So this depletion region provides a high impedance, right? That means I can say here is that depletion region provides a high impedance. High impedance. So, and this P type and N type, there will be lower impedance, right? I can show it like this. There will be lower impedance, and this region is providing high impedance. So there will be this high impedance, and again there will be lower impedance. Can I show the circuit? Can I show the PN junction like this? Are you getting my point? What I am saying? At P type, at this side, I am having some charge carriers. So it is providing me less impedance. Now in between, there is very high impedance, right? In between there is very high impedance, and then again I am having lesser impedance. And then I am applying a battery of V volt. Right? So in between we are having a less impedance. Okay, this I can call, this is depletion region. So R depletion I am calling, this I can call R P type and R N type. So basically R depletion is very greater than RP and RN. Now whatever the voltage that you are applying, now since this resistance is more, that means most of the voltage will go here. Let's just assume if you are applying here 10 volt, that means 9.9 volt will go there, 0.05 voltage will go there and 0.05 voltage will go there, right? So let's just not take the example, but I am saying most of the potential will go across R depletion only. So whatever the voltage that you have applied, most of the potential will go across the depletion region only. And now because of this potential, in what direction we are applying the electric field? In this direction we are applying the electric field, right? So basically the effect of applied electric field E external is maximum at the depletion region and minimum across the charge carrier region. So the effect of the external electric field is maximum across the external region. Okay, what you say that this positive charge will give the force to holes to go in this direction, and will give a negative charge will attract the electrons in this direction, or will give the force to go in this direction. That theory is not correct. Okay, what actually is happening is that this V, because of this V voltage, we are applying some external electric field. Most of the external electric field will be developed across the depletion region only. Okay, now what is happening? Because of this external electric field, this depletion region, this depletion width will be reduced, right? We have an internal field here, and this external field here, and because of this depletion width will be reduced. Why it is reduced? Because the overall electric field is low now. This internal field is there and external field is there. So overall electric field is low now. And if the overall electric field is low, now these holes can move towards the n-type region. So what is happening? Because of the applied electric field, now I have to remove it. Okay, it doesn't get removed, but anything else get removed. Yeah. So what will happen now? Now these holes will move and will come here. These holes will move and come here. Okay. These will move and come here. These will move and come here. Now these will move and go there. And this is how they will go there. Now you will say that here the depletion region will be framed. Is it so? No. Battery will apply the holes. The positive terminal of battery will apply the holes. So these holes will be coming from the battery. So from here holes will be coming. Okay, are you getting my point? So this terminal of battery is to apply the holes, not to give any force. Okay, it's not that they are giving any force to holes and saying that go this side. No, this is not happening. And this terminal of battery is applying, this terminal of battery is giving electrons. Negative terminal of battery will give you electrons. Okay, so this is what is happening in the circuit, in the junction, in the PN junction. What did I say? And the same thing will be happening this side, right? Whatever is happening with the holes, same thing will be happening this side, right? This is giving you electrons. So what is happening? Because of the external field, these electrons now can move towards this side. So here we will have electrons, here also we will have electron. So let me clear it once and then I will draw it clearly. Okay, so these electrons will be moving here. So here again we will have electrons, here we will have electrons, here we will have electrons, and these electrons are moving like this. Okay, so now the depletion width has reduced to this much only. Okay, so let's just understand again what is happening. We applied an external electric field. The most of the external electric field is developed across the depletion region only. So the internal electric field is getting reduced because of the external applied electric field. Now the holes can move towards the N region. Now it will try to move towards the N region. Now this will say that, oh, I don't have hole. Okay, this was my hole, so I will have it here. Now this will say, I don't have hole. This was my hole, so I will have here. Then this will have here, and this will have here. And same with the electron, this will have here, this will have here. Now what will happen? This negative potential of battery can attract these holes. This negative potential of battery, since the width is very small now, okay, and we are increasing the input, we are increasing this voltage. If we are increasing this voltage, that means we are increasing the force. So now this negative battery of this negative terminal of battery will attract the holes, and this positive terminal of battery will attract the electrons, and the current will flow. Are you getting my point? And see one thing, holes are getting attracted in what direction? In this direction. And electrons are getting attracted in what direction? In this direction, because of external field. So in next page, I think I can do it. Okay, I will add a page. So shall I need to write all this? I don't think I need to write all this, because this will not be used in analog electronics. Just to give you the concept, that's why I am telling all this. So I don't think I need to write it. I hope you can remember. Voltage we have applied, external electric field is there, depletion width is getting less. Now what is happening? Because of the external electric field, because of the applied voltage, because of the applied voltage, what is happening? The holes will feel force in this direction, and electrons will feel force in this direction. Why so? Because we are applying a battery of like this, right? So sorry, yeah, so negative will attract the holes here, and this positive will attract the electrons. So the current flows in opposite direction to the flow of electron, and in the same direction to the flow of holes. So this point I can write it. I can write the current flows in the same direction, these are some facts that you need to remember. The current flows in the same direction as the flow of holes, and in the opposite direction as the flow of electrons. You are getting my point? If the holes are flowing in this direction, that means the current will flow in, the total current will be flowing in this direction only, because of holes and because of electrons. This is for hole, P is for hole, E is for electrons. So because of electron, the electron are going that way, that means current will flow in this direction. Holes are going that way, that means current will flow in this direction. So in the forward bias, the current will flow, right? Because of the motion of holes and electrons in a certain direction. These motion are not random. All the holes will be traveling in this direction, all the electrons will be traveling in this direction. Because of the motion of holes and electron in a certain direction, the current will flow from P to N side in forward bias. So in forward bias, the current flows from P to N side. And what is the expression of that current? That is this, Is into e to the power Vd by neta Vt minus 1. Now from where this formula came? Even the EDC guy doesn't need to know the derivation from where this formula came. So no need to worry about the derivation. Just remember what is the diode current, that is Is into e to the power Vd by neta Vt minus 1. What is Is? That is reverse saturation current. What is reverse saturation current? That we will see when we study about the reverse bias. Okay. So for now, just remember this is reverse saturation current. What is Vd? That is voltage across the diode. What is Vt? That is thermal voltage. Okay. And thermal voltage, typically this value is at room's temperature. This is the value of Vt, that is 25.9 millivolt. Okay. And this is the inverse proportion of the temperature, and temperature in Kelvin. Okay. Vt is inverse proportion of the temperature in Kelvin. What is neta? Neta is known ideality coefficient. or factor, we can say non-ideality coefficient or factor. So for okay, I wrote it wrong. So neta is equals to 1 for germanium and 2 for silicon, and if nothing is given, you have to take neta equals to 1. So you got to know what is VD, what is everything. This is your ID. Okay. So what is ID versus VD graph? So for sometimes it is 0. Why it is 0? Because at that time the internal field was more than the external field. At this time, for 0 to this much of value, for 0 to this much of value, the internal field was more than the external field. And when we cross the built-in potential, at that time the current will rise. The current will rise exponentially like this. So this is the curve of, this is the IV curve of diode in forward bias. So this was everything for forward bias. Let's just quickly revise whatever we have studied in forward bias. What we did, we applied an external electric field, external voltage, and that generated an external electric field. E internal was this side, E external was this side. It is continuously reducing the external internal field. So because of that, our depletion width will be reduced, because electron can move towards the p-type region, n-type region. Electrons can move towards the p-type region and holes can move towards the n-type region. So now the depletion width will be reduced, and because of the negative terminal of battery, electron will feel the force, and because of the positive terminal of battery, holes will feel the force, and because of the force, there will be some current that will be generated. Now holes and electrons are moving in a certain direction. Because of that, there will be a current flow from P to N, from P to N side in the forward bias. Okay, so basically from P to N side the current will flow. What is the expression of that current? That is Is e to the power Vd upon neta Vt, that is exponential. But when we study network, when we study analog electronics, we will reduce it to not exponential, we will reduce it to linear. How we will reduce that we will see in the next lecture only. Okay, so we will reduce it to linear. Okay, so this is the expression, this is the curve. For sometimes no current, and when we cross the built-in potential, it will rise like exponential. Okay, so ID equals to Is e to the power Vd upon neta Vt. Vd is the voltage across the diode, Vt is the thermal voltage, neta is the non-ideality coefficient, that is 1 for germanium and 2 for silicon. And when nothing is given, you would always take neta equals to 1. And since this value, this is exponential value, right? Exponential e to the power, let's just take the value of e to the power 6, that will be very high. So since this value is very higher than 1, so sometimes you will see this formula as well. They ignore the 1. Okay, many times they ignore the 1, even we will ignore the 1. Okay, so Vd is actually very high, so that's why they can ignore this thing. Okay, 1 they can ignore. So approximately it is written as Is e to the power Vd upon neta Vt. Okay, so this is the expression. So now let's just see what will happen in the reverse bias. So you are again applying a reverse bias voltage across the PN junction. So what do you think, what will happen now? So in what direction you are applying the electric field? In what direction you are applying the electric field? You are applying the electric field in this direction only, E external. And most of the electric field will be where? Most of the electric field will be there across the depletion region only. So most of the electric field that you are applying, that is across the depletion region only, and it is increasing this electric field. So what will happen? This is increasing this electric field. So what will happen? These holes will be gone again. These more holes will be gone, right? Since the electric field is more, I will just pause it. So this is how the depletion width will be increased. So what is happening? From this negative terminal of a battery, you are giving some electrons. You are supplying electrons. From here you are supplying electrons, right? The electrons are supplied from the negative terminal of battery. And from positive terminal of battery, holes are supplied. So these holes are supplied, right? So from positive terminal of battery, holes are supplied, and from negative terminal of battery electrons are supplied. So what is happening? These electrons are recombining with the holes and making them ions, right? So let us assume this electron is recombined with this hole. Now there was this hole that will come here, because this was recombined, and there was this hole that will come here. There was this hole that will come here, right? Because of these they are getting recombined. Okay, now the electric field is so strong now, this internal electric field, and we have applied an external electric field. This internal and external electric field is so strong that these carriers, these charge carrier holes, can never ever think of moving towards n-type region, and this electron can never ever think of moving towards p-type region, because the internal electric field is very high. Now the electron tries to move there, but in electric field, now this electron is trying to move there, but the applied electric field is in this direction, so it will give a force in this direction. So just stay there, they will just stay there. Okay, okay. So same with the holes. Internal electric field is in this direction, holes will try to go there, but it will give the force in this direction, so they will just stay there. Okay, but there is one more thing, that is there are some minority charge carriers as well. There are some electrons, there are some holes, right? In n-type semiconductor there are minority charge carriers that are holes. In n-type semiconductor minority charge carriers are holes, and in p-type semiconductor minority charge carriers are electrons. Now because of this force, because of this electric field, these electrons can move towards there. These electrons can move towards n-type region, and because of this electric field these holes can move towards p-type region, right? And these holes will move towards p-type region, and this negative battery will attract those holes. Are you getting my point? In n-type region we have minority charge carriers, okay, that are holes, and because of this electric field these holes will feel the force in this direction from n to p, so they will go in the p-type region, and now this negative terminal of battery will attract those holes, so there will be some current flowing, and that current is reverse saturation current. Are you getting my point? So because of that, this was our diode, okay, and this IS current will be flowing, that is known as reverse saturation current, and we are applying the voltage in this direction. So IS is the reverse saturation current, and from where it came, because of the minority charge carriers, because of the, not the majority charge carrier, because of the minority charge carriers, because of minority charge carriers we are having this current. Okay, so whenever I teach device physics, I again and again revise you the things. I again and again tell you the things, because device physics is the topic that we usually forget. Okay, so what is happening? The depletion width is increased, okay, and now there are these holes. Because of the high electric field, these holes will feel a force towards the p-type region, and this negative terminal of battery will attract those holes and will generate some current, but the current will be very less because of there are very less amount of holes and very less amount of electrons. So they are minority charge carriers, and because of that there is always some current, always some small current IS. Now what happens? If we keep on increasing the negative potential, at some potential that we call breakdown voltage, at some potential, at breakdown voltage, there will be a very huge current, in the diode. Okay, you keep on increasing the negative potential, at some potential there will be a huge current in the diode. Okay, and because of that the diode may burn out, but there are some devices that are used to work in the breakdown region only, just like Zener diode. So we will study more deeply about this region in Zener diode, not this region, eventually in this region. Okay, in this region when we study about Zener diode. Okay, so the topics that we are going to study, that will have no use of this region actually. But when we study Zener diode, there will be use of this region. So I will tell you deeply about this region, why the current is increasing like this, why there is a sudden jump in the current. Okay, and after that region, no matter how much you increase the voltage, always there will be a certain voltage across the diode, that will be VB. The voltage will be fixed. Let's just assume our breakdown voltage is 5 volt. Okay, our breakdown voltage is 5 volt. Now if you have applied 10 volt across the diode, there will be a high breakdown voltage is minus 5 volt. Okay, minus 5 volt. So if you have applied minus 10 volt across the diode, there will be high current flowing through the diode, but the voltage across the diode will remain minus 5 only. Even if you had applied minus 20, minus 10, minus 30, minus 40, whatever you apply, the voltage will be fixed across the diode. Okay, so this breakdown voltage will be fixed. The negative potential cannot go higher than this. Got my point? Okay, so this is what happens in the breakdown region. So what did we study? Because of the minority charge carrier, there is always some current. Even if you keep on increasing the reverse bias, but once if you increase the reverse bias so much that there will be a very high amount of current flowing in the diode, and that voltage is known as breakdown voltage, at where this phenomena happens. And what is IS? IS was reverse saturation current, and how it was developing because of the minority charge carriers. So basically we have seen everything for diode. PN junction you can say, or diode you can say, forward bias and reverse bias we have seen. Okay, so let's just revise quickly. In the next lecture we will study diode as a device. In circuit analysis, how we will use it. Okay, and only a few points you will have to remember from this complete lecture. If I summarize, only few points you have to remember. What are the points? Like I can write a summary. Okay, after this page I can write a summary. So first thing, only these points you have to remember. Okay, that's it. First point, how do you denote a p-type semiconductor? P-type semiconductor. How do you denote a p-type semiconductor? Sorry, p-type it is. It will give you an hole, right? And there can be some minority charge carriers. Majority charge carriers are, what are majority charge carriers? These are holes. Okay. And what is minority charge carriers? That are electrons. Okay, this is the first point you have to remember. Second, how to denote the n-type semiconductor? This is electron. Okay, electron will give you electron. What are majority charge carrier? That are electrons. And what are minority charge carriers? That are holes. Then we studied unbiased PN junction, right? Then we studied unbiased PN junction. Let's just take one more page. Point is unbiased PN junction, right? What was happening in unbiased PN junction? This was P, this was your N. So I guess I can copy the diagram. Yeah. This is your unbiased PN junction, right? P type and N type. This was unbiased. Now biased PN junction, P type, N type, and this was depletion region. That was the most important point. This was depletion region. Right? Let me write it again. So this was depletion region. Then what do we do? We applied some bias. That means we give some supply voltage. This was biased PN junction. What did we do? First was the forward. So in forward bias, what did we do? We connected the P to positive and N to negative. This is the potential we provided. Let's just assume the voltage across the diode is VD. So there will be some current flowing through it, that would be ID. So ID approximately is IS e to the power VD upon neta Vt. And here what was happening? Here depletion width was reduced. Depletion width was reduced. In forward bias, depletion width was reduced. Second was reverse bias. Okay. In reverse bias, what was happening? You give an opposite supply, negative to this and positive to this. Okay. This was potential V, and the current was flowing in this direction. Okay. You gave the negative supply. Okay. So the current was reverse saturation current only before breakdown. And yeah, this current is in nano ampere or micro ampere. Okay. So usually in circuit analysis we will ignore this current. So we will just say in reverse bias there is no current. Okay. This is the this has micro ampere or nano ampere only. Okay. And here what was happening? Depletion width was increased. And you can remember the IV characteristics as well. Okay, this was your I, this was your P. Biased diode. Okay, for biased diode, this was your IV characteristics. What was happening? Initially the current was 0, then after a point current rises exponentially, right? This is forward biased. And in reverse bias, what happens? There is always a reverse saturation current. Okay, and then it rises like at breakdown, it rises very rapidly. Okay, so this is your VB, breakdown voltage, and this current is your IS. This was happening in reverse bias. This is everything that you need to remember. That's it. Even if you don't understand any reasoning, all the reasoning I have explained very nicely as far as I understand. Okay, so even if you don't remember the reasoning, that is everything you need to remember. P type semiconductor, how it is denoted, N type, how it is denoted. P and N type, we made a PN junction. Okay, there is the depletion region, because in this depletion region there is this internal field that has this direction, that also you can remember. Okay, internal electric field in this direction. Okay, this is the depletion region. In forward bias, depletion region will be reduced and the current will flow from P to N. And in reverse bias, the current flows from N to P, but that value is very low, and that we call reverse saturation current. And after breakdown, the current will be increased very rapidly. Okay, and in the breakdown region of diode we will be studying in very depth when we study about the Zener diodes. Okay, so here depletion region is decreased in reverse bias. Okay, so this is the complete analysis, and in the next lecture we will be studying diode as a device in circuit, how we will use it and what is the use. So different model of diode we will see, ideal diode, piecewise linear model. So only these characteristics we will use, and we will make different model of diodes by these characteristics. Okay, so that we will be studying in next lecture. So I hope you liked the lecture. So from next lecture things will get easier. This was the toughest part. Understanding the device was the toughest part. From next lecture onwards the things will get easier only. Okay, so let's meet in the next lecture. Thank you.